Greetings everybody. So today we are going to discuss about the electrochemical series. Electrochemical series was proposed by the International Union of Practical and Applied Chemistry, and in that regard, we have previously discussed that they previously, gave an standardized form of electrode potential, which was the reduction potential. That whenever we are measuring the electrode potential, that should be measured in reduction potential as per the agreement of IUPAC. Now coming to the electrochemical series, it was also purposed by IUPAC, and it basically tells us two things. Number one, about the reduction potential or the electrode potential generally. First and foremost, it tells about the electrode potential generally, both oxidation as well as reduction potential. And secondly, it tells about the chemical reactivity of the elements, such that this arrangement provides us the electrode potentials as well as the chemical reactivity of elements. So it's a system of classification of these elements, right? And here in this case, as you can see, in middle of this electrochemical series, we are having an electrode. In middle of this electrochemical series, we are having a electrode which is known as hydrogen electrode, and that hydrogen electrode is known as standard hydrogen electrode, and that basically having its potential as 0.00 volt. When it comes to above the electrode potential, as you can see, as we go above the standard hydrogen electrode, the values of the reduction potential are being decreased, which means it shows that above the standard hydrogen electrode there are elements which have capability to accept which have capability to lose electron rather than accept electrons, because they have negative reduction potential, due to which, as they have more capability to lose electrons than accept electrons, these are more reactive. these are more reactive. So in this case, these are more reactive and they perform oxidation, and these metals are more reactive because they perform oxidation, and since they perform oxidation they lose electron, as a result of which they act as reducing agents. So in that case, above she we are having reducing agent, and below she we are having oxidizing agent. Below she we are having oxidizing agent, and such that below she we have the positive value of reduction potential, such that value of reduction potential is plus 0.10 plus 0.3 plus 0.7 and so on. So in this case, the value is positive. The value of the reduction potential is positive in this case. Value of the reduction potential is positive in this case. So here, as a value of reduction potential positive, indicates that the metals or non-metals or any other elements will tend to undergo a reduction reaction rather than an oxidation reaction, because the more reduction potential showcases more of the capability of the elements to accept those electrons, as a result of which they perform reduction. And since they perform reduction, they have more capability, stronger ability to act as oxidizing agent. As you can see in the diagram, from top to bottom there is stronger oxidizing agent, and from top to bottom there are weaker reducing agents down towards it, and from bottom to top vice versa, there is weaker oxidizing agent, and bottom to top there are stronger reducing agent, right? This is the case. Now on the other hand side, when it comes to the strongest metal, in this case strongest metal in this case is lithium. Strongest metal which undergoes oxidation, or the most reactive metal in the electrochemical series, is lithium. Reason behind it is that it is at the peak of the electrochemical series, and at the peak of electrochemical series, it basically represents the highest negative reduction potential, which means it is having the most reactivity form. So in this case, we can also conclude a point that if there is high amount of reduction potential, then there will be high reduction value, ability to gain electron, which means there will be less tendency to lose electron in order to cause any other substance to react with that particular element. So in that case, those elements which are having capability to gain more of the reduction potential are basically having less value of standard potential, are having less value of reduction potential, and these are considered to be less reactive because they have more capability to accept electron and less capability to lose electron in order to cause the reaction, due to which they are less reactive. But on the other hand side, when it comes to metals basically, let's suppose lithium is having the highest negative reduction potential, highest oxidation potential, which means it tends to lose its electron in order to cause the reduction of the other element, and thus cause oxidation of itself, as a result of which it leads to the formation of a reactive reaction, which means here the reaction is possibly occurring and the reactivity occurring within lithium would be the highest. And as reactivity occurring in the lithium would be the highest, we can conclude a point that l- reduction potential is inversely proportional to reactivity. Reduction potential is inversely proportional to reactivity, and here, if lithium is having the least reduction potential, so it is having the highest reactivity. In this case, this is how we can conclude it. And one more thing I would like to highlight over here is about uh, all the metals which are not in ionic form are considered to be above the standard hydrogen electrode, because they act as oxidative forms, because they tend to oxidize themselves and cause reduction of the other, and they also act as reducing agents. Likewise, when it comes to below hydrogen electrode we are having um, non-metals, as well as those metals which are in cationic form. So those metals which are in cationic form are tin, copper, iron. These all are in cationic form. These basically act as oxidizing agent, due to which these are kept below she standard hydrogen electrode, right? After that, when it comes to another part which I would like to highlight over here, moreover, when it comes to the other part I would like to highlight over here is that they basically tend to tend to come down below the standard hydrogen electrode, because they perform reduction, because they are having positive charge, so they will perform reduction and act as oxidizing agent. And here, as you can see, fluorine, fluorine, basically, it is, I think fluorine is the most, reduction potential having non-metal, and it is having characteristic that it is having the most reduction potential, as a result of which it has the most capability to gain electrons. Reason behind it is that it is the most electronegative element, due to which it tends to grab the electron from other elements, due to which it causes 100% reduction. And this is why it is having the highest value of electrochemical series. Over, when it comes to the other part I like to highlight over here is about some of the applications of this electrochemical series. If we talk about top to bottom the reactivity decreases, and bottom to top reactivity increases. Likewise, uh, if we talk about its application, number one application is feasibility. If we are having the cell potential as positive, it represents that cell will produce some sort of electrical energy and convert the chemical energy into electrical energy. At that point, this reaction which would be occurring would be considered as a feasible reaction, because this reaction occurring would be a spontaneous reaction, and that reaction which would be occurring in a spontaneous reaction would be considered as a galvanic cell reaction, and that would be basically considered as a feasible reaction, because it is causing to occur on its own and instead provide electrical energy. But when it comes to the negative negative cell potential or EMF or cell voltage represents that there is negative cell potential or EMF. Negative cell potential or EMF basically represents negative cell potential or EMF basically represents that the reaction is not able to proceed on its own, so it requires an external source of electrical energy to convert it into chemical energy, such that electrical energy is converted into chemical energy, due to which the cell potential appears as negative, which means electrical energy input is required, and thus this is a sign of non-spontaneous reaction, due to which the reaction occurring would be in an electrolytic cell. Now, if we want to find whether the reaction is feasible or non-feasible, we can utilize electrochemical series. If we talk about copper, copper ion, basically it is an oxidizing agent. Copper ion, as you can see in the chart as well, copper ion can act as an oxidizing agent. It is a strong oxidizing agent, because it will tend to accept electron. And zinc basically acts as the reducing agent, because it tends to lose electron. As a result of which, when we are going to conduct their reaction, copper, as if we are taking copper as the Moreover, when it comes to finding anode will is the one where oxidation occurs. So anode would be considered as the elements above the She, and cathode will be considered as elements below the standard hydrogen electrode, because above the standard hydrogen electrode there is oxidation and below there is reduction, right? Now coming copper is having its anodic value as 0.34, right? But this is the reduction potential. This is what we consider as the reduction potential, so we are taking it as positive. Moreover, zinc basically is having its anodic value. It is a cathodic value, and now zinc's anodic value is basically present over as minus 0.76, minus 0.76. But since it is uh, reduction potential value, we need to find the oxidation potential value. Oxidation potential value would be given as pillar 0.76, right? Pillar 0.76. Now when we are going to add both of these values, the cell potential will be equal to the oxidation potential plus the reduction potential. Oxidation potential with plus reduction potential, plus reduction potential, right? Oxidation potential plus reduction potential, right? This is right. Okay, after that, and then there's another method of finding this. We can utilize a formula which is to take algebraic difference between the electrode potential of cathode and the potential of anode, standard potential of cathode to the standard potential of anode. So in that way, when we are going to take standard potential of cathode and anode, we are then able to gain a value which would be the cell potential or cell voltage. Now in both cases answer will be same, such that if we take 0.34 plus 0.76, then it will give us a value which would be 1.1, I guess, 1.1 volt. And 1.1 volt is positive value, which showcases that the reaction is feasible. If it would be a negative value, that would be a non-feasible reaction. Likewise, if we talk about some other factors, we can also find cell voltage in this case, as we utilize a formula of finding electrode potential. This is how we used to find the cell voltage or EMF of the potential of the cell as well. But when it comes to other factors, chemical processes, these are some electrical processes. When it comes to chemical processes, we can also determine some chemical processes through it, such that we can determine which element undergoes oxidation or loses electron, and which element undergoes reduction and gains electron, in such a manner that here we know that group 1a and 2a elements, these are basically having less number of protons, and these are having the highest value of reduction potential, highest value of oxidation potential, which means they have more capability to lose electrons. Now reason behind it is that they are having you know they are they are having less number of protons, due to which they have less nuclear force, due to which mm, less nuclear force is there, due to which they have high amount of size is there. As a result of that high amount of size, they are less stable and more reactive, because these are densely charged, and because these are less densely charged. So as these are less densely charged refers to the term that here they have more of the empty volume between the nucleus and the orbit, such that they have more amount of due to less charge there is less nuclear force. As there is less nuclear force, the empty space is increased, because there is less nuclear force, so the atomic radii and empty space would be increased, due to which volume will be increased and density will be ultimately decreased. And in that case, the reaction I mean it the atoms which would be obtained would be less stable and more reactive. And as these are less stable and more reactive, they tend to have a higher amount of oxidation potential value and less amount of reduction potential value, such that when we are going to utilize these solutions, they will cause to give us spontaneous reactions, as well as most of the time they will tend to give us spontaneous reactions and convert chemical energy into electrical energy. And they are highly reactive in this case, and immediately react with steam or water vapors. Likewise, if we talk about another example of let's suppose coinage metals, not metals but non-metal elements. Non-metal elements, let's suppose if we are having fluorine, chlorine, bromine, iodine, all of these are non-metals, and these non-metals are placed below the hydrogen electrode, which showcases that they are having they have the capability to accept electron, due to which they are considered to be in the class of oxidizing agents. As a result of being in the class of oxidizing agent, they are going to undergo reduction. And other possibilities are to find positive cations. If we have positive cations such as tin, copper, iron, silver, these all are gold, as well as these are positive cations. And these positive cations indicate that they are acting as oxidizing agent because they tend to undergo reduction, right? And this is how we do it. I mean, this is the application. And the fourth application which I would like to discuss over here is about its reactivity, such that we can find the reactivity of metals with the help of um, um, the electrochemical series. Such that if we talk about the group 1 and 2A metals, group 1 and 2A metals are highly reactive, so kept on the higher oxidation potential value. Reason is told right now, that they have high amount of density, less amount of density, high amount of volume, due to which they tend to remain less stable, more reactive, due to which they have high amount of standard potential of oxidation, right? When it comes to non-metals, not non-metals. Non-metals are already discussed. Apart from non-metals, when it comes to non-metals, apart from non-metals, when it comes to some coinage metals, which includes platinum, gold, silver, hydrogenium, mercury, copper, all of these are basically placed below the standard hydrogen electrode. As these are placed below the standard hydrogen electrode, it basically indicates us that they are having more reduction potential, less oxidation potential. And as these are having more reduction potential and less oxidation potential, these are less reactive. These are less reactive because of the more reduction potential. And reason behind it is that they are having more amount of proton, more nuclear force. As a result of more nuclear force, they have less atomic radii, less smaller size is there. As they have smaller size, due to this smaller size, they are having these are having a smaller size. As these are having a smaller size, this small size will cause them to become more stable and less reactive, due to which these are less reactive and have more reduction potential, which is given. Moreover, when it comes to metals which are near to the hydrogen, metals which are near to hydrogen such as lead, nickel, cadmium, as well as tin, these are metals which are near to hydrogen, standard hydrogen electrode, and these react, but they react very slowly with the steam, water, in order to produce hydrogen gas, right? So these are they react, but they are less reactive. When it comes to other hydrogen electrodes such as those, I mean, one reason that's why coinage metals are less reactive, because of the positive reduction potential. Moreover, when it comes to copper, iron, sorry, these are the coinage metals. And apart from that, when it comes to lead, zinc, chromium, magnesium, aluminum, these are the metals which are having less reduction potential. As these are having less reduction potential, they have more capability to become oxidizing, to become reducing agent and undergo oxidation. As a result of which, as they undergo oxidation and act as a reducing agent, they are reactive, but not as reactive as group 1A elements, because group 1A elements are the most reactive because of their least nuclear force. Apart from that, when it comes to the fifth point which I would like to highlight, is about the reaction with acid. Now reaction with acid is also the same in this case, such that if we are having coinage metals will tend to react less with acids in order to produce hydrogen gas, because these are having less reduction potential. Sorry, these are having more reduction potential, less oxidation potential. But when it comes to the group 1A elements are having more reduction potential, uh, more oxidation potential and less reduction potential. As a result of which they'll tend to react rapidly with H2O uh, in order to produce hydrogen gas, right? And when it comes to other metals, when it comes to these zinc, nickel, lead, um, nickel, sorry, we are having first and foremost lead, uh, tin, and cadmium, cobalt, nickel. These react slowly because these are found near to the standard hydrogen electrode. And nickel, lead, as well as zinc, chromium, magnesium, aluminum, these are those metals which are found more reactive because they have negative reduction potential, right? So they are more reactive and tend to produce hydrogen gas more rapidly when reacting with acids such as H2SO4 or HCl. acid. Last point which I would like to highlight over here is about displacement reaction. That how do they perform displacement reaction? Displacement reaction is performed in such a manner that, let's suppose if there is a salt NaCl, and that NaCl basically reacts with fluorine. So in this case, fluorine is having a higher value in the electrochemical series. Fluorine is present below the chlorine in the electrochemical series. Let's check in the electrochemical series. Chlorine is having is present above and fluorine is present below, such that chlorine is having less reduction potential, fluorine is having more reduction potential. As a result of more reduction potential of fluorine, fluorine has the capability to grasp electrons more rapidly, more readily, more strengthfully from sodium as compared to the chlorine. As a result of which, sodium chloride when reacts with fluorine gas, it will cause the sodium chloride to have the chlorine atom displaced with fluorine and cause the reaction to form sodium fluoride salt plus chlorine gas. Sodium fluoride salt plus chlorine gas. Now rest, we are going to balance the equation and this would be the final equation. So this is a basic answer, displacement reaction occurring. Now here displacement reaction always occurs when a metal which is having its value in electrochemical series, below another metal, is able to displace that particular metal if it is having a reduction potential value as positive. If we consider a reaction of copper sulfate and iron sulfate, copper sulfate and iron sulfate reaction, sorry, copper sulfate and iron, when copper sulfate and iron will react, copper sulfate, iron will be able to displace copper because copper is having less reduction potential, due to which it will iron will be capable to gain the electrons from the sulfate, as a result of which the iron will be able to gain the electrons from the sulfate and now form iron sulfate and displace copper, due to which the product obtained would be iron sulfate and copper as a free state metal, right? And after that, when it comes to other part, if we take zinc and magnesium, now magnesium sulfate is a salt. Let's suppose we are taking magnesium sulfate. Now magnesium sulfate reacting with zinc will not cause to give us, this reaction would not be possible. Reason behind it is that here zinc is also having an oxidation potential, negative reduction potential. Magnesium is also having reduction potential. Although zinc is having less reduction potential as compared to magnesium, but still it is having reduction potential negative, showcasing that it is having the capability to lose electrons but not having capability to gain electrons, due to which zinc will not be able to displace magnesium. So this would be a reaction which would not be possible, not feasible. Moreover, if we talk about a reverse reaction of sodium chloride with fluorine, if we talk about sodium fluoride and chlorine reacting, so in that case, chlorine will not be able to displace fluorine because chlorine is above the fluorine in the electrochemical series and has less reduction potential, as a result of which it will not be able to attract those electrons towards it in order to form the compound sodium chloride once again, due to which it would be a non-feasible reaction. Now last point which I would like to highlight over here is that about the reactivity of lithium, because if we take lithium or any other alkali metal, that when it is found in free state, in free state its electrochemical potential, electrode potential value, reduction potential or oxidation potential value is zero, which means it does not react. But when it comes to its solution in water, when we are taking it in water, let's suppose we are taking lithium in water, then at that moment lithium in water would be considered to be in the form of ion, and that would be monovalent cation, and that monovalent cation will be forming lithium ion plus one electron, right? Lithium ion plus one electron, right? This is how we form it. Now this lithium ion which is found within the water molecules, within the water, will tend to react with H2O. Now lithium basically, even though it is having a small size, it is having a small size as compared to, in groupic consideration, we are having lithium smaller size than other group 1a elements such as sodium or potassium or rubidium or francium. These are having smaller size. So here lithium is having smaller size than all of these elements because of being at the top at the group 1A. And at that moment, uh, you know, if we talk about their size, they are smaller in size, as a result of which, when they tend to react, as these are smaller in size, uh, they are having high amount of charge surface density, such that as they are smaller in size, they have less volume. As they have less volume, they have more density, and that density would be considered in terms of charge surface density, such that there would be high amount of charge of high amount of nuclear force due to small size, due to which there will be high amount of charge surface density, right? And if there's highest amount of charge surface density, that high amount of charge surface density will be attract of lithium will be attracted by the negative part of H2O. Negative part of H2O, which is the OH ion, will tend to attract the lithium cation towards it. As a result of which, the lithium cation being attracted towards the OH part, negative part of the H2O molecule, will tend to form an interaction. Attraction would be developed. That attraction would be known as dipole ion interaction, and that dipole ion interaction developed will lead to an exothermic reaction. It will lead to an exothermic reaction, and that exothermic reaction formed will tend to release an energy, and that energy would be considered as the enthalpy, and that enthalpy would be enthalpy of hydration or heat of hydration, delta H, heat of hydration or enthalpy of hydration, right? And when the enthalpy of hydration is released, since lithium is having high amount of charge surface density, that would be having a high amount of uh, attraction by the OH ions of the H2O, due to which there will be a stronger dipole ion interaction formed. As a result of the stronger dipole ion interaction formed, there will be a high amount of heat of hydration released, and that high heat of hydration released will now be considered, you know to have increased the capability of lithium to perform oxidation, such that if the heat of hydration which is released over here will now tend to increase the capacity of lithium to perform oxidation, such that its oxidation will be further increased by the heat of hydration which is released within the aqueous solution of water, due to which it will cause to increase the heat of hydration and ultimately the oxidizability or oxidation power of lithium, right? And after that, this is all about why lithium is so reactive, as well as why other metals are so reactive and why not. uh, yes, this is all about the video. Hopefully we'll meet in another video.